Again, I'm very happy to be here, to be able to celebrate Ivan's retirement. So I'm going to tell you about some work that I did recently with Pearce, that I'm still doing with Pearce and Klümper. Still not published, but this will happen soon. But of course, before I start, I want to talk a bit about Ivan, because Ivan has had such a great role for all of us, and especially for me. So I remember the first time that I met Ivan was in 2004, when it was my first year as an undergraduate here in physics. And of course, I had a first class in linear algebra. And from my previous experiences, I found this topic to be so boring. I was like, oh my God, I've done this in CJEP, and now they're making me go through this again here. And I had very low expectations when I stumbled across this class by Ivan, which was just blew my mind. Right? It was like, I could not believe that somebody could have so much passion and energy teaching about this topic. And of course, since then, my impression of linear algebra has changed. And of course, after that, I followed more classes by Ivan, and then I realized that it was really Ivan who was the special thing about classes. It was not like all my courses at university were not like Ivan's courses. Ivan's courses were always extremely well prepared, and I could see that he was in front, and he was very smart, and he would, so his class was like a masterpiece. I was like, and so later on, so I think the second time I encountered Ivan was during my second summer here at the University of Montreal, so between my second and third year. And I was doing an internship in theoretical physics. And then I learned that there was going to be a reading group organized by Ivan. I was like, oh, that's quite interesting. And then during the whole summer, once a week, somebody would present. First, there was Ivan about the 2D easing model. Then there were others, postdocs and students. And this was very interesting because I learned very many new things. And I was again amazed that somebody could be so devoted to supervising students. So, of course, this was a very important moment for me, because it's what actually brought me to approach Ivan and then said, oh, I would like to work with you. And then this is how it started. And then I started doing research with him. And again, he was very invested and really helped me to develop my research skills, because at first, well, you've never really done research, but Ivan, it was there. And I always felt like Ivan had worked on my project more than me, like every week. And I was like, oh my God. But in the end, eventually I grew, and I was able to do my own research and to develop my own results. That was great. Yeah, so this picture, clearly not the best picture of Ivan. So it was taken in 2013. Okay, so we were both visiting Canberra, visiting David Ridout in Canberra, and we had climbed this Telstra tower and came out to see this beautiful panorama. I have a second picture, also from the same moment, where we can see that none of us have aged in the last 10 years, right? And a fun thing about this is that I recall exactly what we talked about when we were on this tower. Two things that I remember from this conversation. The first was that I was telling Ivan that I have vertigo, so like I'm afraid of heights, and he said, "Oh, me too, but it's a bit special. I'm afraid of heights, not when I'm at the top and looking at the bottom, but the other way around." And I found this very special because I had never seen anything like this before, right? And the second thing that I remember, which was quite fun, was that when we got out of the tower, Ivan sneezed, okay? And then he said, I have this thing that when I'm in a dark place and come out of the sunlight, I sneeze all the time. And then I researched this, and I realized that there's something called the photic sneeze reflex. So it only works when you go into the sunlight from somewhere dark. And like after I learned about this, the article said there's about 15 to 30% of the population that had it. And then I started having it. I was like, oh no. And then I remember, like, this happens to me all the time, especially I'm in Paris having coffee, take coffee, go out to enjoy it. And then you have your hot chocolate or coffee, and then you're going to sneeze. So you have to be careful. So hopefully from here on, I can infect some of you as well. And next time you sneeze in the sunlight, you can all think about Ivan. So, okay, so I want to tell you about this work that I'm doing with Pearce from Melbourne and Andreas Klümper. And you'll see that there's, oops, that's not what I want to do. I want to just move the mouse. Okay, so this is also closely related to things that I did with Ivan. So I'm going to tell you about, so the plan of my talk, first part, I'm going to define certain models of percolation. And the goal of my talk will be to study one of these models in particular and use the integrability structure, which is section number 2. Okay, so use the integrability structure to make some exact calculations and then we're going to see that I'm going to compute certain transfer matrix eigenvalues, compute partition functions. And in the end, it's going to allow me to say something about the CFT and the universality of these models. Okay, so models of percolation. So, okay, so in this slide, I'm defining two kinds of percolation models, side percolation and bond percolation. Okay, so the first one is side percolation. So here you can see it's actually defined on a triangular lattice. So you can see these hexagons, but each one, normally you would draw a site instead, and you would see that every one of these sites would have 6 neighbors, as you have on the triangular lattice. But here I drew them as I drew the faces. Okay, so these hexagons, they can be colored 2 colors, either white, so I would say uncolored, or colored purple. And to these 2 local choices, I give probabilities P or 1 minus P for each one of them. Okay. And then when I draw an entire configuration here on the torus, well, the configuration, which I call sigma, well, the weight is going to be of the full configuration is P to the number of sites right here, and times 1 minus P to, well, the number of NS is the number of colored sites, and MN minus NS is the number of white sites. Okay. So a very simple model, side percolation. I can do the same thing, but now for bond percolation. So here it's a bit different. Instead of having these hexagons which are colored, here I'm on a square lattice, and I have these bonds which are colored or uncolored, again, with the probability P or 1 minus P. And then the weight of the configuration is just the product of the local weights. Okay. So this model has been very well studied. I think I barely need to introduce it for this audience, but there are tons of applications. And for phase transitions, this has been like the first example. For example, we heard about it in the talk from David, who said, this is the simplest model, you should start there. Okay, so, but one feature of this model is that the partition function is trivial. So you just sum over the configurations of the weight of the configurations, and it's just 1. And this is due to the fact that all of these random variables are independent. Okay, so very simple model in this respect. And actually, the interesting things about this model are about these non-local clusters. So you can see that I have these either sites or bonds, or they group together to form colored clusters or uncolored clusters. So in my talk, I'm going to talk about 2 kinds of geometries, but with periodic boundary conditions. The first is the torus, but I'm also going to talk about the cylinder. But whenever we look at these models, we look at what we consider them first in the plane, like either as a square or a parallelogram, and then in the end, we're going to close them in one direction to obtain a cylinder, or in the second direction to get the torus. Okay. So an interesting observable is not the partition function, but rather some crossing probabilities. So what's a crossing probability? Pi h of p. So it's the probability that I can cross from left to right by following only the colored bonds or sites. Okay. And this is something non-trivial, and it's something non-local. These percolation models, they're all in 2 dimensions. They all have a critical value of this small p, okay, which is called the critical threshold, okay, and denoted here by PC. And it turns out that on different 2D lattices, the value of PC can be different. However, for the 2 models that I introduced on the first slide, it's well known that it's exactly PC is equal to 1/2 for both of them, both side percolation on the triangular lattice and bond percolation on the square lattice, 1/2. If instead I had considered side percolation on the square lattice, and it's not 1/2, and it's actually a number for which we don't have a closed form. We can evaluate it numerically, but we don't know exactly, we don't have a closed form for this time. Okay. So apparently they seem to be different, but they have some very common features. And in particular, so this crossing probability, so this is a figure taken from the very famous paper by Ivan with Langlands and Pouliot. Okay, so what happens here? So this is the plot of this crossing probability as a function of small p. Okay, and you can see that, of course, so when p is 0, well, there's none of the sites. So it starts at 0 and ends at 1, and then there's a value at PC where this will change. And the different curves, okay, they're actually numerical experiments done on sizes of size 2, 4, 8, up until 128. And the one with 128 is the one which has the sharpest slope. Okay, so eventually when this becomes infinite, okay, so what you expect is that this will converge to a step function. Okay, and this, yeah, so they disappeared in this old paper by Ivan. So here you can see that this is actually done for side percolation on the square lattice. You can see this because this number here is precisely where the transition occurs, just below 0.6. Okay, and nonetheless, there's something interesting. So of course, the derivative grows as n increases. Okay, and how fast does it grow? Well, this has been measured, and it's now something accepted that this grows as like the derivative at the critical value grows as n to the 3/4. But what's particular here is that this 3/4 is the same for all three models. Okay, even though the value of PC is different, this exponent, this critical exponent, is exactly the same. Okay, and this can be quite surprising when you realize this. And in the end, the reason why this happens is because these three models are believed to be described by the same conformal field theory. My next slide, I have a second example of such an observable. So the so-called percolation probability P of P. So let's read it together. It's the probability that a site at the origin is in a cluster of infinite size and the limit mn goes to infinity. So I look at one of these sites, I take the size of my lattice to become infinite, and then I ask what's the probability that there's it's inside an infinite cluster. And this one behaves like this. So below PC it's 0, and at PC it starts growing until it reaches 1. And again, the critical exponent, it occurs when you look at how fast this curve starts growing. So as you approach the PC from the right, well, it grows as there's a critical exponent, which is 5/36. So this is, again, the same for all three models. Side percolation on the triangular lattice, square lattice, and bond percolation on the square lattice at the critical value, which is different in all three cases. So in all three cases, this exponent will be the same, but this kappa will not. So this kappa is non-universal. So what's remarkable about these models is that two of them are actually integrable. Okay, so, and for one of them, this one here, this has been known for a very long time. Okay, and the integrability, you can first map this model to a model of loops, which are just the contours of my percolation clusters, and I can remove. This is really a bijection. So this is really like a gas of loops, and this goes back to the work of Temperley and Lieb, actually. So you can take this, describe it in terms of the Temperley-Lieb algebra, and it's related to the 6-vertex model. This one on the left, well, this one is also integrable, and this is what I want to tell you about today. This is something that I learned not so long ago from a paper by Garbali and Inhoys that can also formulate this model in terms of something which is integrable. So in my talk, you're going to see Yang-Baxter equations and transfer matrices for this model. Okay, so the way it works here, so you can see it, I'm going to talk about this in more detail afterwards, but it also goes by a map which draws the contours of my clusters, but now this one is dilute, so the loops are not everywhere. The one in the middle is actually believed not to be integrable, right? At least we don't know how to do it, but we believe that it's not integrable, so we cannot do all the nice calculations that I'm going to present. So indeed, these percolation models are believed to live in the same, to be described by the same CFT. They're believed to be universal. This was something that Louis Pierre talked about from the early work of Langlands, Pouliot, and Saint-Aubin. And the fact that two of them are integrable allows us to make very many checks to see whether this is possible or not. Okay, and this is what I want to talk about. Okay, so one slide on logarithmic CFT. So this, for critical percolation, it's known that the central charge for the CFT is C equals to 0. And here for C equals to 0, you have these conformal dimensions, delta R comma S. And typically, if you have a rational CFT, so these are the conformal weights, and then R and S are certain integers in a restricted set. For this model, it's just this small set. Okay, so R can be 1 and S can be 1 or 2. And it's a trivial CFT. You have one representation, it's one-dimensional, and that's all you have. And this is completely trivial. Okay, so you won't learn anything from a rational CFT for this model. Instead, you have to study a logarithmic CFT, where you have many more fields. For example, maybe they can be in this extended cast table where R and S can be infinite, but maybe they can also be fractional numbers or even any real number. Okay, so in this CFT, so you're going to have some primary fields, some logarithmic fields, and some two-point correlation functions that will be either not only with power laws like here, but also with some logarithms. So our goal in this project was to figure out what are all the possible fields that occur in this theory, and I'm going to show you how integrability allows us to answer this question, at least partially. Okay, so in the development of CFT, a very important object is the partition function. Okay, and so here I'm going to define a generalized partition function, because indeed the first one that I showed was just z equals to 1, nothing to be learned there. Okay, so instead, generalized partition functions, here I'm defining them on the cylinder. So here I have my side percolation model on the cylinder. So you can see that it has a width n, a height 2m. And then you can see that I'm choosing certain boundary conditions where I'm fixing one color on one side, and then I'm also fixing on the other side, but the rest is arbitrary. And this, it's a cylinder because the top and the bottom are identified together. Okay, so I'm defining a partition function, which I call z of alpha. Z of alpha is the sum over all configurations over this lattice. And then alpha is some real or complex parameter. And then n of sigma is the number of non-contractible loops. The non-contractible loops are those that wrap around my cylinder. So one of them starts here and goes around and connects back here. Okay, so in total in this diagram, I have 3 such loops. Okay, this reflects the fact that I have 4 clusters. So this configuration would have a weight in this sum alpha to the power 3. Okay, so this is different from what I had before, where I was giving potentially different weights to different colors. Here, they're all given a weight 1. So I'm going to define 2 partition functions, z0 and z1. Z0 is when I fix the same color on the left and right, and z1 is when I have a different color. Okay, so it turns out that you can solve this problem in terms of transfer matrices, but not just one transfer matrix, but a family of transfer matrices here that I write as a calligraphic B. It depends on an integer small d, and this small d ranges between 0 and n, where n is the width of my lattice. So using the usual techniques of Yang-Baxter, well, you can compute z0 and z1 as follows. So you take the transfer matrix, these transfer matrices, put them to the power m, and then you sum over d and multiply by some Chebyshevs that depend on this weight alpha that I have here. And the only difference between z0 and z1 is that the values of d are summed over even or odd values. Okay, so in other words, if I want to compute these partition functions, I need to compute the eigenvalues of these objects. Okay, so I told you how it works on the cylinder. What about on the torus? So on the torus, it turns out that I can define the same kind of generalized partition functions weighted with a weight that depends on the number of non-contractible loops. But now I'm going to define not 1, not 2, but 4 partition functions, which I label as PP or AP, PA, or AA for periodic or anti-periodic. Okay, so what does that mean? So here I have a 4x4 percolation lattice. And periodic means that as I move along an axis, well, I get exactly the same configuration. And likewise, again, along the second periodicity axis. So this is periodic. But I can do something a bit different. And along my vertical axis, as I move along, the next copy is everybody's flipped. So colored goes to uncolored, and likewise. So in this direction is periodic, but anti-periodic in this one, PA. So likewise, AP, I have anti-periodic and periodic, and then anti-periodic in both directions. In all cases, you have exactly 2 to the n to the number of sites. So here there will be 2 to the 16 diagrams. But of course, choosing periodic versus anti-periodic, what it changes is how many contractible loops there are. So here you can see that there are none. And here there's at least 1. Okay. So 4 different partition functions on the torus. Okay, so I've defined my models. Now I want to tell you why these models are integrable and what we can do about this. So I told you that this comes from the work of Ninhuys and Garbal. So you start with your configuration of side percolation, and then the first part of the map. This is going to be a map in 3 steps. The first part of the map will be to every time that I have like 3 faces that are adjacent, I draw a small triangle, and then if they're of the same color, I don't draw anything inside. But if they're not, then I'm going to draw inside my triangle a small loop segment that draws the contour. Okay, so that's the first step. It goes from here to here. The second step to get this is that I'm going to operate a rotation on the bottom row in one direction. Then this gives me this bottom row, and on the top one, I rotate in the other direction. Okay, so when we do Yang-Baxter integrability, we like to have models defined on a square lattice. So here now I get the model defined on a square lattice, where I have 9 possible tiles, which are actually dilute, right? The curves do not go everywhere. And then on one side, I have a boundary which is straight, and on the other side, this boundary has these triangles in a zigzag. The third part of the map now is I just want to forget about where they travel. I just keep track of how they connect the top and the bottom. Okay, so I forget about the history of these curves, and I just see that this first curve here connects to so this one connects to this one. So this gives me like a diagram, which is a diagram of the dilute temporally algebra, where I'm going to have these curves that connect points pairwise, but also some sides can be left empty, and we're going to call these vacancies. Okay, so this map in 3 parts goes from a configuration of my side percolation, and it gives me an element of the dilute temporally algebra. And as okay, so the same thing happens when you have periodic boundary conditions. The only difference, so I won't go through the whole map, but the only difference is that in the end, the diagrams that I get when this side is connected to this side, well, my curves, they can connect to this left side of my box and reappear to the right before they connect to the bottom. Okay, so as many of you know, so this in the last 15 years, Ivan has really focused on the representation theory of these algebras. So here I'm going to talk about the dilute temporally algebra, for which Ivan has worked a lot with Jonathan Beltec in particular. So what are these algebras? So they're defined in terms of these diagrams. So connectivity diagrams like these ones. Okay, so I have, so dilute temporally, I have a number n, which here would be 6, and then this number beta, which is a loop weight. Okay, so so a diagram like a connectivity diagram is a box where I have n nodes on the top and bottom, and then they're connected by pairwise by sides or occupied by these vacancies. Okay, and whenever I want to multiply them, well, I just draw one on top of the other. Like here, this is C1, this is C2. Then I pull the strings, I get this diagram when I look at how the top and bottom are connected. And then because I have a one constructible loop, I erase it and put a weight of beta. And so the result here gives me this. This is, of course, non-commutative. So if I multiply in the other direction, well, there's an extra rule that says that if I have a loop segment that is attached to a vacancy, then I set the result to 0. So this is clearly not commutative. Okay, so this algebra is defined on the vector space of its connectivities with this product. Okay, and yeah, so this has been studied in particular by Ivan, and then you can look at certain representations, which are called standard representations, which are labeled by a number d. Okay, so d is a number of defects or through lines, and so this d goes between 0 and n. So there's a family of representations, and when beta is a generic parameter, these are all irreducible representations, and they give you a basis of all the possible such representations. There's also something similar when you're considering a periodic algebra, where now these segments can cross from the left to the right. So this one I add a small p for periodic, and they have representations that are standard, which are labeled by an extra parameter, which we call the twist, omega. This is a real parameter. Okay, so these representations are useful because, as I'm going to discuss, all my information about the transfer matrix and the model of side percolation, if I have these representations, I'll have all my information. So I want to define a transfer matrix for my model of side percolation. This is how it's done. So these transfer matrices, they're going to be elements of my algebra before being matrices. Okay, so here, this would be my double row transfer matrix calligraphic D, and my single row calligraphic T. And the way they're done is they're done to precisely reproduce what I had at the end of my map, right? So they're done to reproduce what I had here. They're exactly of the same shape. Okay, so how are they defined? So first, you'll see that everywhere where I have a triangle, this triangle with the square inside is a sum of 4 diagrams. Okay, so why is this an element of my dilute temporally algebra? So to get, these is actually a sum of 4 to the number of triangles, so 4 to the 4n plus 2 diagrams. This is a lot of diagrams. A lot of them will be actually 0. Whenever I have a loop segment that is attached to a vacancy, this will give me 0. So it's actually much less than 4 to the 4n plus 2. And every one of them is understood as an element of my algebra. So this is the sum of connectivity diagrams. In this case, they all have a weight 1, because here there's only a weight 1s. And likewise, this one is an element of my periodic algebra. So these are elements of the algebra, but I can actually define matrices by looking at what happens in the representation. So in the standard representation, say V and D, well, these actually give me matrix realizations of these objects. So I don't have one transfer matrix, but I have a family of transfer. Okay, so I've defined a transfer matrix, but this is not yet enough. I need to insert it in a larger family that commutes using the Yang-Baxter equation. And the way this is done is by studying a more general model that is called the A22 loop model. So in this model is defined in terms of a face operator, which is usually in the vertex language called the R-check matrix, is a sum of the 9 diagrams of the dilute temporally on 2 sides. and I have certain coefficients or Boltzmann weights, rho 1 to rho 9. Okay. So these are chosen, and these are parameterized in terms of two parameters, u and lambda. And lambda parameterizes the loop weight as follows. And the parameter u is the spectral parameter. Okay, and these are chosen in such a way. Okay, so the function s of u, sine u divided by sine lambda. These functions are chosen in such a way that the Yang-Baxter equation is satisfied. So the Yang-Baxter equation in this case is an equation in the dilute temporary algebra. And this small dashed line is the identity of this dilute algebra on one side. Okay, so that's nice. And with this, we can construct commuting transfer matrices. So either with periodic boundary conditions or when we have a boundary. And when we have a boundary, we have to add these boundary K matrices here, which are linear combinations of two diagrams. Okay, so these are actually chosen to satisfy the boundary Yang-Baxter equation. And it turns out that with all the familiar ingredients, you can show that these form two separate families of commuting transfer matrices. Okay, and again, these are not elements of my algebra, but you can see them as actual matrices in the standard representation. Okay, so I have these transfer matrices, and now my goal is going to be to compute their eigenvalues. But before I say this, I want to tell you that this is related to another model called a vertex model called the Isergen-Korepin model. This is a 19 vertex model where the R-check matrix, it can be obtained easily from my operator of the previous slide. This would be the corresponding R-check matrix. Okay, so later on, in a few minutes, I'm going to tell you about how I'm able to compute eigenvalues of my transfer matrices of my loop model. Is the same question as answering the question as computing the eigenvalues of the transfer matrix of this Isergen-Korepin model. Okay, so indeed, so the case that I'm interested in for side percolation is a special case where lambda is pi on 3. When lambda is pi on 3, then beta, which was -2 cosine for lambda, is equal to 1. And then my phase operator here, it actually simplifies, because when I set lambda to pi on 3, there's an overall factor that appears, which I can remove. And then I can define a renormalized R-check matrix, where the difference now is I draw this as a small square rather than a small arc. Okay, and then I get again a sum of 9 possible faces. Okay, with weights that are simpler. Okay, and moreover, if not only I set lambda to pi on 3, but also u to pi on 3, well, then these weights simplify further. And now I have 8 of them, which are equal to 1. And only the last one is actually equal to 0. So before I had 9 diagrams, and in here I only have 8, all of them with the weight 1. And I can write this in terms of my triangular operator, which I defined before, right? My triangular operator was just a linear sum of these 4 diagrams. And this is why this model at pi on 3 is related to side percolation. So indeed, so what happens when I look at my transfer matrix at lambda is equal to pi on 3? Well, it turns out that, yeah, so the boundary condition here, my K matrix becomes just the identity. And then these are, again, now they depend on the spectral parameter. So they commute at different values of u and v, okay? And finally, when I set u equal to pi on 3, I recover precisely the transfer matrices that I need for side percolation. Okay, so this one is exactly the same. So this calligraphic t is t hat of pi on 3. The other one has a factor of 1/2, but this is very simple. It's just because the boundary condition is slightly different, but you can show that they're exactly equal. Okay, before I had a straight segment here and then some triangles here, and this is why there's a factor of 1/2. So this is sort of inserting, this is giving the Yang-Baxter integrability structure to the side percolation model. So now our goal is to compute the eigenvalues of these objects and use the integrability toolbox to compute these eigenvalues. Once this is done, so once I have the eigenvalues, I can compute the partition function. So this side is a summary. And then where the simplest case is when we set the weight of the non-contractible loops alpha to be equal to 2. So on the cylinder, I give this formula earlier where these were Chebyshev polynomials. And so this is just the Chebyshev polynomials when the argument is equal to 1. So this is not simpler than the usual case. But when you're on the torus, then things simplify drastically. And the 4 partition functions, you can compute them again in terms of the traces of your transfer matrix over the standard representations, where the twist parameter is either 1 or -1. And the only difference between periodic, and periodic antiperiodic is this sign. Okay, and likewise for AP and AA, it's this sign. And then the numbers D over which this is summed are even or odd. So again, I want to compute my partition functions. I need to compute the traces of these transformations. I need to compute their eigenvalues. Okay. So this brings us to, yes, section 3, eigenvalues and partition functions. So it's known how these eigenvalues, the leading eigenvalues, the ground state, the next one, how they behave as a function of n, the system size. So there's an asymptotic expansion for log of di. Di is the ith eigenvalue of this transfer matrix. Okay, so there's a first term, which is called a bulk free energy, then a surface free energy. But the conformal part, the interesting data about the CFT appears on the third term, which is proportional to 1 over n. And so our goal is to compute these constants here, delta I. Okay, so for this, we go back to, so there are various ways that people can compute these numbers. But the way that we use is to use the equivalent of the beta ansatz and Baxter's TQ equation. And in this case, this TQ equation is a functional relation that involves D and Baxter's auxiliary function Q. But instead of just being TQ, like usual for the 6-vertex model, it's TQQ. And then we have something which is quadratic in Q on the right-hand side. So the beta roots are the zeros of this function. And then from this equation, we can easily write down the beta ansatz equation. Okay. And now our goal is to solve these systems. And we have done this, and it's a long yet beautiful calculation, which you will not see today. But what we do is we take this equation, transform it into a set of nonlinear integral equations, and then massage them until we're able to compute these numbers here, delta I. And then we find a formula for delta I, where this is just the final result, as a sum of 3 integrals. These are integrals over paths in the complex plane, okay, from the origin to some non-zero value. And then for different eigenvalues, they have different values of delta I. And this appears in 2 places. The first is the constant here, which we can compute. But most importantly, it's in the contour. So the endpoint is the same. It goes from 0 to this endpoint. But this contour goes around in the complex plane in a non-trivial way around the 2 poles, 0 at 0 and -1. And depending on the eigenvalue, the path will change. Okay. So now what we have to understand is understand which paths this takes for different eigenvalues, and then we can measure this conformal dimension delta I. So so we've done this both. So here I presented how it worked on the cylinder, but on the torus, yeah. So for my 2 geometries, it works in the same way. I have basically the same equations in the 2 cases, with the difference that for T of U, I have 2 conformal weights that I can measure. Okay, so once we have this, well, we can use this. We have some analytical arguments. We compute these analytically for certain eigenvalues, and in other cases, we use this numerically to see what are these numbers. And then we want to compute the trace of d to the m. So the sum over the eigenvalues, d to the power m. And then we want to see what this gives as a sum. In computing these, what I need to do is to exponentiate this. So then I would get an exponent, the exponential of the first 2 terms, which turn out to be the same for all the eigenvalues. And here I just keep the conformal part in this equation. And then we're able to express the traces in terms of characters of the Virasoro algebra in this parameter Q, which depends on my spectral parameters and my geometry M and N. Okay. So with this, we can compute the partition functions, okay, as a power series in Q. And here I just give the final result for on the torus, where I have 4 partition functions, okay, for my 4 different boundary conditions. They're all expressed in terms of these characters half of J, which are related to these. We have an explicit expression that comes from here. We're able to produce this conjecture, which results in this conjecture. So we were able to find this expression. And the remarkable thing, which is the punchline of our last punchline, is that we find exactly the same partition functions for the side percolation as those in the common bond percolation in the previous. So in our previous paper, we studied from 2015, we studied the side bond percolation in the square lattice. And we oriented the lattice in a way that is natural for integrability. So it's a square lattice that's tilted by 45 degrees. And then this is the cluster of
something wrong is with the sound in the online translation.
The sound, I don't think he hears. They hear.
So in our last paper, what we did is we studied the bond percolation. And then on this lattice, there are 2 kinds of. It's on the boundary. This is on the cylinder. So this is the edge of my cylinder. This direction is to the right. On the side of my cylinder, I can suppose that my bonds are wide, or I can suppose that they're not wide. And it turns out that with this bond percolation, you can always define a dual tree. Okay? And then this dual tree basically goes everywhere, where my main independent tree has to go. And having something which is y on one side for red means it's unwise to green, and the other way around. So the partition function that we compute for side derivatives when I have the same color on both sides turns out to be exactly the same as the one that we have created when the same color is wired on both sides. And likewise, when it's a different color, you get exactly the same power law in Q, and eventually in Q1 as well. So indeed, on the torus, we have four partition functions that we have for side relation, bond partition, and they exactly coincide. Okay. So this is very strong. This is a very strong argument for the fact that these two belong to the same CFT. It's by no way proof. Basically, we compute time, like an infinite number of conformal dimensions, and they're exactly the same, and their derivatives are exactly the same. So this is very strong argument to say that these two models belong to the same. So this is an overview of my talk. So we studied side percolation, the integrability structures on the triangular axis, and we computed the eigenvalues of the model, and then we found identical partition functions for the model of side and bond. So this is the end of my talk, and I'll end my talk with very nice picture I was taken recently. I'll thank you, so in the name of everybody in this picture.
Merci, Alexi. Any questions in the audience first?
So you have the result of the partition function, but as far as the conformal dimensions are involved. So
the mic.
Sorry.
Yeah,
but I'm curious. So the conformal dimensions for which you have this big calculation, is there I would think naively that people know all the conformal dimensions that appear in percolation. So do you have any new numbers appearing, or do you have new results concerning the multiplicities, or?
Yes, our results, what they say is not only for specific ground state, but it's the integrated representation for this A22 model. We know exactly the character, not just the leading ones. We know exactly this here. So first for the traces, we know exactly what the characters are, and they're different from the ones that occur in just the sequence model. And then when we recombine them correctly using the so-called Markov trace, then they give exactly the same one that's for bond partition. So
okay, so there's some info about multiplicities and stuff like that, which allows you to reconstruct the.
Exactly.
Okay.
You know exactly the result of that one side percolation and exactly the one that's for bond partition, which we're not.
Any other question? Ivan?
The characters are those of the Verma. Oh, I was thinking about the next slide. Yeah, they're all the Verma module. There's no quotient of these.
Okay, so again, I was changing slides because here's where you can see the Verma module characters. So first, when you press E, you get these cat characters, which are actually related to the cat representation, which are not Verma modules. And here you have a sum of, when you have an infinite sum of two, the product of two Verma characters. Of course, it doesn't tell you if these are reducible or not, because we only have the character. But it doesn't give us the full information about the representations that come out. We just know the way it's.
But what about the next transparent when you write the partition function in terms of are the chi characters of Virasoro?
They are, but they're sums, right? If I just have one power divided by this, it would be a Verma module, but these are sums. So it's one smart way of collecting these together in family.
And all the weights are in the cat table, or they are not?
Okay, so if we're looking at atoms on the cylinders, they all are. If we're in the torus, you have to look at the atoms in the cat table, and they're all. But in principle, we gave the solution for alpha is equal to 2. We changed alpha. So I forgot to say here, but here you see that if I change alpha, I would have a continuous, the first number here in my delta r comma s would be a continuous number. If I change alpha, I would have a continuous
And can you check modularity?
Yes, so indeed, so in these four partition functions, all four of them are actually modular invariant. Only the first one, I would say, is the true modular invariant in the sense that when you decompose it as a series in Q, it has only positive integer coefficients, and the other three, they have negative. This is due to the fact that we're imposing a strain on that periodic boundary condition, which is non-null.
But that doesn't change modularity. It's only
All right, I think it's a good time to stop. Thank you, Alexi, again.